Yeah, so thank you very much for the introduction. As mentioned, I'm a PhD student at the University of Erlangen-Nuremberg, and I would like to talk about the modeling and simulation of artificial standing waves. So first I would like to introduce the team, which consists of mathematicians and engineers under the guidance of Michael Döllinger, and our focus includes studying surfing from a scientific perspective. We use computational fluid dynamics to analyze various use cases in surfing, not only looking at surfboards or fins, but also the dynamics of waves themselves. So we get valuable support from the Nürnberger Dauerwelle, whose surfing experience helps us to understand whether the results we simulate can actually be observed in real-life scenarios. So first, I would like to give you an overview of our expertise in the area of surfing. So we started with a numerical investigation of lift and drag forces on surfboard fins in a 4-fin configuration at various angles of attack. So what you basically can see here is the flow field. We have our 4 fins, and with CFD simulations, we basically calculate the forces acting on each fin. So this was published back in 2020 by a former colleague of mine, and actually 1 year earlier, in 2019, we also investigated the same thing, looking at a 3-fin configuration. And here you can clearly see the significant differences in flow behavior at various angles of attack. So if you are interested, read the papers and reach out to us if you have any questions. However, numerical simulations should also always be validated experimentally, and to achieve this, we 3D printed our own fins and embedded pressure sensors into them to experimentally validate the drag and lift forces we already have simulated. And then we have integrated this fin into a surfboard and had a surfer to perform various turns on the Nürnberger Fuchslochwelle, as you can see here in this video. We measured the pressure over time, which we will use to compare these experimental results to our numerical work. So this is also this will also be published soon. Furthermore, we are using optimization methods to calculate the ideal force application point on surfboards. So this helps us to understand. So we use optimization methods to calculate the ideal force application point on surfboards, and this helps us to understand where the surfer needs to be positioned on the surfboard to ride down the wave with minimal balance adjustments. So this would look like this in this video. And we basically combine CFD simulations with optimization methods to solve this problem. So that covers what we have done so far in the area of surfing, considering surfboards or fins. And a new topic we are exploring is the modeling and simulation of standing waves, similar to those, similar to the wave in Nürnberg, the Fuchslochwelle. And one major challenge with standing waves is the formation of those recirculation zones, which can be dangerous for surfers. If a surfer falls off the wave, they may have difficulty being washed out of this zone and could potentially be pulled back towards the wave or even underwater. And our task was to replicate this phenomenon in numerical simulations, allowing us to experiment with adding obstacles to minimize those recirculation zones without significantly altering the wave's characteristics. So, as I mentioned, we are focusing on the Fuchslochwelle in Nürnberg, and here in figure A you can see a satellite image of the wave and the model sections. So we have an inlet basin, we have our concrete channel with our wave module, and we have our outflow basin. And this setup was designed with 3D CAD tools, which we can see here. So this 3D model serves as our simulation volume for conducting our flow simulations and represent all important parts like the inflow basin, the outflow basin, the concrete channel, the wave module, inlays, and our chicanery. So here is a more detailed view of the wave module. The flow moves from left to right. The water is flowing down this plate, being redirected by the kicker and then hitting on this inlay. And the key parameters such as the flow rate, the inlay length, or the kicker angle and so on, which you can see here in this table, were all kept constant across all simulations. And our approach to reduce this backflow was to introduce a chicanery on the inlay, which you can see here, which looks a little something like this. So our default configuration, as shown here on the top left side, without any chicanery, serves as our reference and represents the current state of our wave. So all simulated configurations are compared to this setup to evaluate whether certain modifications effectively reduce your recirculation zones or not. And we aim to simulate various configurations to find the optimal position on the inlay for minimizing backflow. So for instance, we installed the chicanery at 1 meter, measured by this edge here on the inlay, at 2 meters and 3 meters. We additionally tested configurations where we removed sections on the left and the right side on the inlay module, focusing only on the central inlay section, and installed the chicanery again at 1, 2, and 3 meters. We also ran simulations with asymmetric configurations, so for example by installing additional chicaneries at the side wall, which you can see here in this top, or positioned them at different positions on the inlay or in different V-shapes to the front or the back. So we have a total of 15 configurations. So as I mentioned at the beginning, and this is a really technical talk, I apologize for that. So we used a 3D simulation of the flow, especially a multi-phase flow, and the software we used was RCCM+, where we numerically solve the Reynolds averaged Navier-Stokes equations. And to do this, we need to divide our simulation volume into small subregions known as a grid. And in our case, our grid has 2.2 million cells. And since this is a highly computational intensive process and would take several years on regular computers or desktop PCs, we ran the simulations on a supercomputer with 64 nodes. And to give you an idea of the scale, one node is about as powerful as 5 standard computers. And we essentially ran on 320 laptops at the same time. Despite this, each simulation took an average of 19 hours to complete. I'd like to briefly show you the governing equations. So those are the Navier-Stokes equations, and they describe an incompressible flow in general. So we solved this numerically to simulate our flow behavior, and essentially it's based on Newton's second law of motion, where we have mass times acceleration on the left side, and we do have the sum of our forces on the right side. So those forces include internal forces such as the pressure field or viscose forces within our fluid, as well as external forces, which is in our case the gravitation. So this partial differential equation has no known analytical solution. So however, if any one of you manages to find one, there is a $1 million prize which you can win because it's one of the 7 millennium problems. This is what our simulation volume looks like. So we intentionally choose not to simulate the inlet basin to save computation time. As I mentioned, it took around 19 hours on a supercomputer, and we don't fully understand its effect and assume that it's not significantly impacting the flow behavior and the wave formation. So here at the front, we have our inlet where the water flows in, and we have here in the back our outlet where the water flows out. And since we are dealing with a multi-phase flow, we also need to define an air outlet, which is shown here in orange, which represents the top boundary of our simulation domain. So the rest of our simulation volume is defined as a no-slip wall, which means that the velocity of our fluid at the walls is 0, as in real life. Now, how do we know which of our configuration achieved the desired behavior of reducing this recirculation zone? So to address this, we define a volume here behind the wave, which is shown here in green, where those backflows occur, and we calculate the vorticity. So the vorticity essentially indicates the power of a vortex, and looking at the image here on the right side, we can calculate 3 different vorticity components in x direction, in y direction, and in z direction. And the z direction vortex is the most interesting for us, as it represents the backflow we aim to minimize. So this table shows all of our results. We see here the wave height and the 3 vorticity components in each spatial direction. So at the top in red, we see our default configuration representing the state before introducing the chicanery, and in green, the top 3 configurations we have simulated. So these include the setup with the chicanery at 2 meters along the inlay, the asymmetric arrangement, and the combination of the side chicaneries with a chicanery at 3 meters. And in general, the higher our wave height is, and the smaller the vorticity value is, the better for us. So one immediate observation is that the wave height is maintained or even increased across our top configurations. This is important as a higher wave provides a larger surface area for surfing, but we can also see that the vorticity value in z direction was reduced by over 50% in all of our top 3 configurations. So I will now explain this in more detail, showing you the result of the flow fields. Here we see the flow field of the default configuration on the left side, and the resulting flow field after installing a chicanery at 2 meters. And the 3 images represent different slices along the width of the concrete channel, so here at 25, 50, and 75%. And the flow moves from left to right, so the kicker here redirects our wave. The colors indicate the velocity of the fluid, increasing from blue to red. So what we see here in our default configuration is the recirculation zone extends roughly 10 meters. And by installing our chicanery, we can reduce this region to about 3 meters. So this reduction occurs as the jet created on the kicker and impacting on the inlay, which we see here, is redirected upward, naturally limiting this recirculation zone. It's also important to note that the fluid velocity remains consistent, which we also can observe here as well if we compare both results with each other. Here is another result, again comparing the default configuration on the left side, but this time with the chicanery positioned at 3 meters here on the right side. And we do observe essentially the same effects as in the other configuration. The jet is deflected upwards, leaving no room for backflow, thereby reducing the recirculation zone. And in this case, the backflow area is slightly larger compared to 2 meters, as the point where the fluid impacts the inlay is a bit further forward. And the reason I'm showing this is the following. From our simulations, we observed that installing a chicanery can significantly reduce the recirculation, and based on these insights and our results, it is decided to install the chicanery into the real setup. And here you can see the drained wave module, the wooden replica of our chicanery, and the final modified chicanery geometry, which was installed. And this chicanery had to be placed at 3 meters as no other space was available on this inlay. And at this point, I would have hand over to Buffy, who is not here because he got sick. I will do my best to report about the improvements in real life we have achieved through our simulations, but I have to tell you, I have never stood in my life on a surfboard, so I will do my best. The first improvement is that previously inflows exceeding 8.5 cubic meters per second created a strong backflow, making it hard to swim against this backwash, which led to surfers dive deep to get washed out of the recirculation zone. So the modification with our chicanery allows the operators of the wave now to operate the wave with more than 8.5 cubic meters per second without the risk to be pulled back into the wave. Even for first-time surfers, now a flow of 9.5 cubic meters per second is possible without any safety concerns or little safety concerns, which also leads to a bigger wave, hence a bigger surfing area. This also leads to surfing slots, mixing surfers with different experience levels into one slot, which was not possible before the installation because this backwash could be a higher risk factor for beginners. I want to show you two videos how fast surfers get washed out. I have no idea if this is a fast washout or if it takes too long. I mean, it's just after the installation of the chicaneries, you have to decide if it is a fast process or not. So, as a conclusion, we could not only replicate the wave behavior and minimize the recirculation, surfers also report that our simulation and the effects we simulated can be observed in real life. So, if you'd like to learn more about our work or are interested in a collaboration or would like us to model your wave and try to optimize the flow behavior, please contact Michael Döllinger or me at any time. So thank you for your attention, and I'm happy to answer all your questions at my best behalf.